Welcome back to Tokenization from Scratch. In the last two episodes, we built byte pair encoding from scratch and made it encode and decode losslessly. Today we make it production grade the way GPT actually does it. We run BPE on raw bytes instead of characters, which guarantees there is never an unknown token, and we add a Regex pre-tokenization step so merges never cross word boundaries. Let's build it. Quick recap of episode 3. We wrapped everything in a tokenizer class. Brain learns the merges, encode applies them in the order they were learned, and decode walks a vocabulary dictionary back to bytes. Round trips were lossless. But two real-world problems are still lurking, and both are solved by the same two ideas we cover today. Here are the two upgrades. First, operate on raw UTF-8 bytes. Every byte is just an integer from 0 to 255, so the base vocabulary is exactly 256 tokens that can spell anything. Second, pre-split the text with a regular expression before BP runs, so a merge can only ever happen inside a word or a punctuation run, never across them. Let's start with the bytes. Watch how little code this takes. We take a string with an accented letter and an emoji, call .encode UTF-8, and get a bytes object. Wrapping it in list gives us plain integers, every one between 0 and 255. That's the whole trick. Instead of inventing a vocabulary of characters, we use the byte vocabulary that already exists. And bytes decode reverses it exactly. Here's the real output. The string is 7 characters, but 11 bytes, because the accented E takes 2 bytes and the robot emoji takes 4. Notice the largest ID is 240, comfortably under 256. Every character, no matter how exotic, dissolves into ordinary bytes, and decoding gives the exact string back. Nothing was unknown, nothing was lost. Here's the pipeline visually. Each character becomes 1 to 4 UTF-8 bytes, the plain H is 1 byte, the accented E is 2, the emoji is 4. Those bytes are already integers from 0 to 255, so the base vocabulary is exactly 256 tokens. Because any text in any language reduces to bytes, a token is never out of vocabulary. That's the unknown token problem, gone for good. Why 256? A byte is 8 bits, and 2 to the 8th is 256 possible values. UTF-8 guarantees that every Unicode code point, every letter, accent, emoji, and script on Earth can be written as a sequence of these bytes. So 256 starter tokens can spell anything. BPE then sits on top, merging the most frequent byte pairs to build longer, reusable tokens above ID 255. Now the second upgrade. If we run BPE on one flat stream of bytes, it will happily merge a letter with the punctuation or space next to it, giving you junk tokens like dog with a period. The fix is pre-tokenization. Split the text into sensible chunks first, words, numbers, punctuation, runs of white space, and only let BPE merge inside a chunk. GPT-2 and GPT-4 both define those chunks with a single regular expression. Here's the difference. On top, without pre-tokenization, the bytes for dog, the period, and the next word all sit in one stream, so BP can merge G with the period across the boundary. On the bottom, pre-tokenization puts each word and each punctuation mark in its own box, and pairs are only counted inside a box. So G and period can never join, and the subwords you learn are clean and reusable. This is the actual GPT-2 split pattern. It needs the third-party Regex module, not the standard library Re, because it uses Unicode properties like \PL for any letter and \PN for any number. Read it left to right, common English contractions, then an optional leading space followed by letters, or by digits, or by punctuation, and finally runs off white space. The optional leading space is the clever part. It keeps the space glued to the word that follows. And here's what it produces. The contraction I' splits off on its own. Each word carries its leading space, so the token is space got, not got. That's how the model learns that words usually start after a space. The number 23 is its own chunk, the accented word stays intact, and the exclamation mark is separate. BPE will now run strictly inside each of these pieces. Here's the full encoder, reusing the getstats and merge helpers from episode 2. For each Regex chunk we encode to bytes, then repeatedly apply the lowest indexed learned merge, that is, the earliest one we learned, until no more apply. Because we loop chunk by chunk, merges physically cannot cross a boundary. We concatenate the results, and that's our token stream. And the payoff. We trained 20 merges on a tiny corpus, then encoded a string with an accent and an emoji. It tokenizes to 13 IDs instead of 19 raw bytes. The learned merges compressed the common bits like the and cat. Decode returns the exact string, lossless. And the last line is the whole point. A Japanese word the tokenizer never saw still encodes and decodes perfectly through its raw bytes. No unknown token, ever. Let's recap. Running BPE on UTF-8 bytes gives us a fixed base of 256 tokens and removes unknown tokens entirely. Regex pre-tokenization splits the text into words, numbers, punctuation and white space before BPE, so every merge respects word boundaries. Our tokenizer now handles accents, emoji, and scripts it has never seen. Next episode we add the control tokens a model actually needs, end of text, chat turn markers, padding, and build a simple chat template. See you there.